All right, let's get underway. Welcome, everyone. Thanks for coming. I bid you a good morning because in my time zone, it's 7:45 in the morning. I'm glad you've been able to attend this session known as correctly calculating min and max and more, with the subtitle, What Can Go Wrong? Let's start by having a look at what I like to call the big picture. So, as we all know, the C++ standard library, about 25 or more years ago, selected OperatorLess to be its ordering primitive. And it actually even spells that primitive in several different ways, for example, standard less. But today, first I will demonstrate why that OperatorLess and its aliases must be used with care, even in seemingly simple algorithms such as max and min, and we'll look at others, of course. We'll discuss the use of OperatorLess in other order-related algorithms and show how easy it is to make mistakes when using that primitive directly, no matter its spelling. And along the way, I'll also present a straightforward technique to help us avoid such mistakes. I'm rather fond of this quote by Alexander Stepanov. One of the amazing things which we discover is that ordering is very important. Things which we could do with ordering cannot be done effectively just with equality. So, with that background, let me share with you some of my early attempts. An intuitive approach might say, let's write min and max as function-like macros in the C style using pound define. And it would look more or less like this. But those of us in the C++ world don't particularly care for macros. We prefer functions. So we can repackage min and max as functions. But now, of course, we're going to need one overload for every possible type. Here I'm showing that, min and max for int, but we would want to have min and max for float and for double, and perhaps for character, and perhaps for standard string, and so on. So the next logical step in the progression is to lift those functions and turn them into function templates. And here I'm showing them in the C++20 style. But those templates, which I've reproduced here for your convenience, do have just a few issues. For one, the parameter passage, which is by value, is, as you know, potentially expensive. For example, for arguments that happen to be large strings. Also, these templates permit the arguments to have distinct types. And when that's the case, it's quite unclear what the return type should be. And actually, it's even unclear how to compare arguments that are not of the same type. My standard example for this is, one argument that is a signed type and the other one being an unsigned type. We'll talk about that more in the near future. But that's a non-obvious comparison in all cases. And of course, the major concern is always, are these algorithms correct for all possible values? If they're not correct, they're really not useful. Well, the cures for these are mostly straightforward, and the standard library specification embodies the cures. We can enforce consistent types by having a named type parameter and use it consistently. And we can avoid potentially expensive copies by changing the call by value into call by reference to const, but nonetheless call by reference. And after those adjustments, what we have looks approximately like this. And of course, analogously for max. Here we're using t as the underlying type, and both our parameters are of type T, well, reference to T, but nonetheless, they will be T's. But please do recall that if you happen to be calling such functions or function templates with R values, L value references to R values do have a subtlety. If you call min, let's pretend that X and Y have member functions named calc, which return temporaries, we're going to get back a reference to one of those temporaries. So we can, of course, copy from that, and that's fine. But if we're trying to take the result by reference, by the time we're done with this statement, what we will have in R is a dangling reference, because those temporaries will be gone at the end of this full expression. Nonetheless, that's sort of on a side topic. So what's actually wrong with the algorithm? The problem is that none of the code that I've shown you so far is what and I'm in good company because Alexander Stepanov agrees, none of that code is right. So let me show you one last time. I'm going to stop talking for 10 or 15 seconds. Please have one final look at these templates and see if you can identify the misbehavior. Did you notice that each of these returns B in the case that A and B are equal? This is what I have in mind. And of course, the question that we should all be asking ourselves, why should max and min of the same two arguments ever give us the same result? It just seems intuitive that if min were to give us one of them, max should give us the other one. And yet, here's a case when both give us the same result. Now, I found someone who made the claim that it took Alexander Stepanov 15 years to get min and max right. I believe that's a bit of an exaggeration, but it did take him some time. Now, what specifically is wrong? The claim is that these algorithms do not properly handle the case of equal arguments. Now, I found somebody on Stack Overflow who wrote the following. He said, at CPPCon 2014, which was the first CPPCon, committee member Walter Brown mentioned that standard max returns the wrong value when both arguments have an equal value. And that's correct, I did say that. But the key question is at the end of the quote. Why should it matter which value is returned? Now, I must confess, I've heard this observation, this question for many, many years, actually for decades. Usually the argument runs something like this. Equal values are indistinguishable. They're equal after all. So it shouldn't matter which one we're going to return because they're indistinguishable. So this really is not an interesting case, barely worth discussing. But I'm sorry, because for min and max and related algorithms, these opinions are superficial and they're incorrect, except in very simple cases. So let me share with you what Alexander Stepanov himself says about his own mistake. If you're having trouble with the audio or with his accent, please watch the left side of the screen.
How stupid could one be? I mean, one spends decades working on all these orderings and writing min in the most generic way, and then he writes max, and he screws it up. And the person is me. And You'll say, well, but nobody will even remember that. Oh no, people will remember for centuries because that's the max in the standard library. So for as long as C++ stand, my shame will be publicly visible.
So, in the master's own words. So let me give you an example, because there are, it turns out, many types that do distinguish equal values. And here is what I would consider to be a bare bones example. A new type, which I've named student. It has two data members, a student's name and a student's ID, and a static data member I've named registrar. And the only use for the registrar is to initialize the student's ID. We have passed the name explicitly, but the ID comes implicitly from the registrar. And the only other member of this type that I've provided is an operator less than that can compare two students. And notice the simplicity of the comparison. We look only at the name. We do not consider the ID. For the purposes of less than, the ID is not considered salient. Since each student variable, every variable of this type is now going to have a unique ID number, even values that are equal are distinguishable. So two students may have the same name, but they're nonetheless distinguishable because their IDs are different. Therefore, it can matter a great deal which of the two is going to be returned by min or by max. So, of course, the next question is, how do we address this issue? From the perspective of mathematics, we have the notion of a monotonically increasing sequence. And we all recognize that a sequence that is monotonically increasing, meaning it never decreases, it only ever increases, is considered sorted. But the converse is not true. And the simplest counterexample is a sequence of identical values. Such a sequence is sorted, but it of course is not monotonically increasing. It's not increasing at all. So instead, what we should be saying is that a sequence is sorted if and only if it is non-decreasing, assuming we want it in increasing order. And this is what allows us to have equal items in a sorted sequence. C++ actually embraces this viewpoint, and there's the citation, if you care to look it up, because it says that a sequence is sorted if, for every iterator I and non-negative integer n, indirect I plus n less than indirect I is false. Okay? In other words, it's non-decreasing. Okay. So what's the important insight here? If we're given two values, which I've named A and B, and we're handed them in that order, A, then B, unless we find a reason to do otherwise, min should always prefer to return A, and max should always prefer to return B. In other words, never should max and min return the same item. When the values A and B are in order, min should return A and max should return B. And when values A and B are out of order, min should return B and max should return A. Now, we can say this even more succinctly by saying that we should always prefer algorithms that are stable, and particularly so when it costs us absolutely nothing to provide that stability. Now, please recall what we mean by stability. An algorithm that deals with the order of its items is known as, or is termed stable, if it keeps the original order of items that compare equal. In other words, a stable algorithm guarantees that for all pairs of equal items, A and B, A will precede B in the output of the algorithm whenever A preceded B in the algorithm's input. So in consequence, here is what I recommend. For min, the body should look like that. We should have a predicate that says when A and B are out of order, we return B, otherwise we return A. Now, I understand some people would prefer to code this by asking, are A and B in order? And if they are, return A, otherwise return B. But I prefer the formulation that says, is there a reason to do otherwise? Remember, min should always prefer to return A unless there's a reason. So is there a reason to do otherwise? If so, return B. Otherwise, by default, we return A. And of course, analogously for max, when A and B are out of order, we return A. Otherwise, we prefer to return B. So what is that out of order predicate? Well, it looks like this. When handed X and Y, they are out of order whenever Y is less than X. So when are they in order? Well, when they're not out of order. And in my experience, the out of order predicate tends to be more useful when there's work to be done. The in order predicate turns out to be more useful when we're trying to avoid doing work. Okay? In my experience, out of order is the more useful of the two. Now, so far, I've confined myself to talking about min and max, but the same ideas I've discovered are broadly applicable. So let's look at some examples. Here is a very simple, fairly classical merge algorithm. We are given a pair of iterators to the first input sequence, assumed sorted, a second pair of iterators to a second input sequence, also assumed to be sorted, and of course, we're given a destination, which I've named 2. You'll notice the body first takes care of 2 special cases. If the second sequence is empty, we return the result of copying the first sequence. There's no more merging to be done. Otherwise, if it's the first sequence that's empty, we return the result of copying the second sequence. There's no more merging to be done. So all the interesting work happens in the else clause. The analogous logic, we should prefer to take from the first sequence, and we need a reason to take from the second. So again, we write to the destination, well, if indirect B1 and indirect B2 are out of order, we'll take from B2, but by default, we'll take from B1. And this is what I mean by analogous logic. Let's look at some more examples. Here's a very simple algorithm that's given 2 items and sorts them in place. So we're given A and B by reference, not constant, of course, because we potentially mutate them. If A and B are out of order, we swap them. Otherwise, there's nothing to be done. And the post condition, of course, is that A and B are now in order. Very straightforward, I hope you'll agree. For those of you who would prefer to use the in order predicate, the body might look like this. If A and B are in order, we can do an early return because there's no work to be done. Otherwise, we swap A and B. and we still establish the post condition. Now, what happens if instead of sorting 2 items, we want to sort 3 items? So here's a sort 3 algorithm. It may look a little unusual to you if you're not familiar with C++20. I'll walk you through it briefly. If it says, after sorting A and B by calling sort2, it so happens that B and C happen to be in order, we can do an early return. We're done. We've guaranteed that A and B are in order. We've established that B and C are now in order. We're done. Otherwise, we know that B and C are out of order, or we would have done the early return, so let's swap B and C. If after doing that, it so happens that A and B are in order, we can again do an early return. Otherwise, we swap A and B, and now we're done, and we've guaranteed that A and B and C are now sorted. By the way, although it's an unfamiliar presentation, perhaps, did you recognize bubble sort? That's what this algorithm implements. This is bubble sort on 3 items. So after I wrote this, I went online to have a look to see how other people might have coded this sort3 algorithm. And on Stack Overflow, I found this. And I was sort of taken by its complexity. If I were to ask the question, is this correct? It just seems like there are an awful lot of cases. There are 6 separate cases that I have to check. And I even had to elide some of the code to make it fit on the page. You can tell where the comments are. I elided some code to make it fit. So it turns out that I can answer the question rather quickly just by looking at the 2 lines I've highlighted here. If A is less than B, then if B is less than C, we can do an early return because A and B and C are sorted. That's true. That's not wrong, but it's not exactly right. Consider the case that A and B and C are all equal. This algorithm does not properly handle that case because every other of these cases, the remaining 5, every other case does some work. It either does a sum swap or some half swaps to do a rotate. So my claim is that this algorithm does strictly more work than necessary much of the time. The point, of course, being is that operator less than is not a substitute for an in-order predicate. If this had said in order instead of saying less than, it would have been better. Further, it's clear that this algorithm is not stable. When they're all equal, we go out of our way to do some work that we don't need to do. Things that were in a certain order will not be in that order any longer. So this is non-stable. So there are 2 main takeaways so far. The first is the observation that by itself, operator less than is not sufficient to tell us whether its operands are in order. What it can do by itself, operator less than, is sufficient to tell us only whether the operands, once reversed, are out of order. Okay? All right. Now, having made those observations, I'd like to discuss a little more about operator less than, because it turns out, as we observed right at the beginning, operator less than is spelled other ways as well. There are many standard algorithms that don't use operator less than spelled that way. Often, standard library algorithms specify an overload with an extra parameter, traditionally named comp, such that the algorithm calls comp on X and Y to decide ordering instead of saying X less than Y. So let me take one example. There's an algorithm, it seems to not to be particularly common in use, but it is a useful algorithm nonetheless, is sorted until. And it is given a pair of iterators, and internally it uses operator less than. But there is an overload that takes an extra parameter named comp, and internally it calls comp, where the first overload uses operator less than. Now, let me tell you just a little bit about that is sorted until algorithm. The specification in the standard says that it returns the last iterator I in the closed range first through last, for which the open range first comma I is sorted, and it does this with linear complexity. Now, that's the specification. In other words, we note that this invented iterator I induces adjoining partitions, one from first up to I, and the second from I up to last, where the former is known to be sorted and of maximal length. Okay, so this is a restatement of the specification. And a while ago, I went and I looked at several standard library implementations, and all the ones I looked at had some iterator I in their implementations. However, let me restate it in an equivalent way, without I, but in a manner that I think is better for those of us who think algorithmically, which I think is all of us. Let's treat from somewhere up to first as a partition that we know is sorted, and that it have an adjoining partition from first to last whose order we know nothing about. Now, what we can do is iteratively advance first, as long as indirect first is sorted with respect to its immediate predecessor. And at that point, by construction, the first of the partitions up to first has maximal length, so all we have to do is return first. And this works even for empty cases. Let's look at some code. This is my earliest implementation, the version that uses operator less than. It looked like this. We make sure that first to last is not empty. If it is, there's no work to do, and we can strictly return first, because first will equal last, and it doesn't matter which one I return. If it's non-empty, then there's at least one item. One item, by definition, by itself is sorted. So we'll record by saying previous equals first, initializing previous. Then we'll increment first. Notice this is as if I had said prev equals first plus plus. But I like to avoid post increment, as do most implementers of standard library algorithms, because there's an implicit copy whenever you do a post increment. So we strongly prefer pre-increments whenever possible. And then the body of this loop simply asks, is indirect first less than indirect pre? Now, it turns out that's correct. But over the years, and I did this well over 20 years ago, over the years, I revisit algorithms, not only to refresh my memory, but to see, are there new facilities that let me implement them better or differently, and so forth. And every time I went back to this algorithm, I found myself asking myself, does this mean I'm asking whether these things are in order or out of order? And it always takes me some small amount of time to figure it out. And I had to do that again and again and again. So as I hinted at earlier in this talk, I now prefer and recommend to use what I called a named order predicate. And my code has evolved into this. I introduce out of order. Here I do it with a lambda, which of course is available ever since C++11. And I want to show you a quick little tip. Notice that out of order here is being passed the iterators, which are usually cheap to copy, rather than the dereferenced values, which might not even be copyable for all we know. Okay, so I call out of order on prev comma first. And we can use this approach even before C++11 because we could always define a macro to do the equivalent. I showed this code to someone about 6 or so months ago. And the only question they asked me, they said, well, why didn't you undef the macro at the bottom? And it turns out I didn't bother doing that because I had put this in a module. And of course, macros don't leak out of modules in C++20. So I became lazy in my old age. But nonetheless, this is an option. The standard says that the declaration compare comp is used throughout the algorithm's header, of course, as a parameter denoting an ordering relation. Compare is a function object type whose call operation gives us true if the first argument of the call is less than the second and gives us false otherwise. In other words, comp induces a strict weak ordering on the values. And the final observation, for all algorithms that take compare, there is a version that uses operator less than instead. Now, I'd like to just share with you very quickly that in my opinion, these names comp and compare are just too general. They're not wrong, but I consider them insufficiently specific. I would strongly have preferred the name, for example, less than, or LT as an abbreviation, which I may use if I don't have enough room, or even precedes would be a better name. Now, even when we have a version of an algorithm that takes an explicit predicate, I still recommend adapting it via what I've called an order predicate. So that version of is sorted until would look approximately like this. Notice I've renamed out of order to something like iter out of order, following the model of the standard library where we have both swap and iter swap. One takes values, one takes iterators. So this is a convention I recommend. The standard library isn't entirely consistent because other places we use the name indirect as a prefix to indicate the analogous. But nonetheless, what I've done is adapt this precedes predicate into iter out of order. And now it's very clear what's going on. If the values given by prev and first are out of order, I've gone as far as I can go. I have found the first unsorted item, and I can return first. Now, there is another technique because we can avoid overloading by using a single template with judicious default arguments. It would look approximately like this. I haven't shown the body because the body hasn't changed. Notice this version of is sorted until has two defaults. It has a default template argument, standard range is less, and it has a default template, a default function argument, namely empty braces. So two questions probably come to mind rather quickly. The first being, what exactly is standard range is less? And the second, do we need both kinds of defaults arguments? So let me answer those in turn. What is standard range is less? Well, it's the name of a class declared in the functional header. And it looks approximately like this. I've simplified it a little bit for exposition. But notice it has a call operator as a function template that's a member of the class. Please notice this does a heterogeneous comparison. We allow two types, a class type T and a class type U. Heterogeneous comparison. A variable of this type is a function object because, of course, it's callable through that operator parens, the call operator member template. I should point out, and I'll talk a little bit more about this later, that there is also standard less as contrasted with standard ranges less. The major difference is that it's a template and it has an operator parens that is strictly homogeneous. Nowadays, most of the programmers I talk to seem to prefer the design of standard ranges less. I'll compare them for you a little bit later. But let's get to the second question. If we adopt this, do we really need both kinds of default arguments? Well, let's have a quick look again at the declaration of the algorithm, and then let's consider a call to the algorithm. So here's the declaration, same as before. And then here's a sample call. We have an array named A of length n, and we're going to call is sorted until with a plus 0, comma, a plus n. So my first question is, what type will be deduced for FWD, which I pronounce forward? It's supposed to be a forward iterator, right? So take a few seconds, see if you can deduce, as the compiler would, what type will be deduced for forward. I hope that was pretty straightforward. Forward, of course, is deduced as an int star because both a plus 0 and a plus n are int stars, are pointers to int. But notice that this call did not provide a third argument. So the default kicks in. So what type will compare be deduced as? And again, give it some thought. I'll be back in a few seconds. Okay? Well, of course, the answer is going to be the default. Standard range is less, taken from the default template argument. Now, let me remind you that a default function argument is never used as the basis for type inference. Never. Okay? And that's what allows calling code to default construct the third argument, namely standard range is less instantiated. Okay? Now let me introduce a third question. If you take a careful look, why doesn't the standard library use default arguments like this? Why do we have this pair of overloads in the STD namespace? And the answer is, well, the short answer is, it's prohibited. Unless it's explicitly specified to take default arguments, your implementer can't put them in. And here's the actual language. Implementation shall not declare a non-member function signature with additional default arguments. There's a citation in case you care to look it up. Okay, so why not have this consolidation? Why do we keep both overloads? And the answer is that if we did it, it's problematic. It took me a while, but I found this paper from almost 25 years ago, N1070, which has this very pertinent sentence. The difference between two overloaded functions and one function with a default argument can be observed just by taking a pointer to function. You can tell the difference. So an implementer is not allowed to use this technique unless the specification says that it can. There's a further reason for this. Suppose a client makes a call and specifies a type. This is not a recommended practice, but suppose it happens. Consider a call that specifies the type, but not a value. So here's a function template G that has appropriate defaults for both kinds of parameters. But what if it turns out that the specified type is not default constructible? Now the call is in trouble and can't compile. All right? So the algorithms in the standard namespace, the STD namespace, do not and are not allowed to use default arguments like this. It turns out the specification in the standard ranges namespace is different, and default arguments are part of the specification. All right, so let's talk a little bit more about the standard library's disguises, as I call them, for operator less than. We've mentioned some of these before, but as best I can tell, there are a total of 6, not counting operator less than itself. Here's the list. Let me go through it with you briefly. I've mentioned the class template less, found in the functional header. It's been there since C++98. And notice its argument types are homogeneous. It takes 2 values of the same type, T, whatever T happens to be. Now, starting in C++14, the standard introduced a specialization of that template named less of void. That specialization cannot occur by type deduction. There are no values of type void. So this could never previously arise. So this particular specialization was introduced as the standard library's version of heterogeneous comparisons. It can take arguments of types T and U that don't have to be the same. In the ranges library, all of this still in the header functional, introduced with C++20, we have a class, as I showed you earlier. It's named rangesless, and it has a member template that permits the less than comparison to be heterogeneous. At the same time, in C++20, we got a function template named cmp-less, which I pronounced compare less. We put it in the utility header for a reason which I can't understand. But it accepts any two integer types, I and j. So it's a heterogeneous comparison, but it knows, for example, not only how to compare two ints, but how to compare an int with an unsigned int, which is non-trivial. We'll revisit this in a few moments. In C++11, in the cmath header, we've got an overload set named isLess, which is heterogeneous for any two arithmetic types. And in 2008, the IEEE standard promulgated a specification which it named total order, spelled with a capital O. And in C++20, we adopted that by reference as part of the specification of the strong order customization point in the compare header. And this is an ordering on two values of the same floating point type. So this is a homogeneous comparison. And let's look at some of these, at least my versions of them. So here's my version, slightly edited, of standard ranges less. This is not what the standard specifies, but I'm not sure why we don't. So given two types, L and R, we take them by forwarding reference. If it turns out they're both integer types, then I'm going to call the compare less that I'll talk about in just a moment, which I mentioned on the previous page. Otherwise, if they're not both integer types, but they are both standard arithmetic types, then I'm going to call isLess in the standard library. And I'll discuss that in just a moment. Otherwise, I'm just going to do a less than comparison. But of course, I have to forward the two values since I took them by forwarding reference. So this is approximately my version of standard ranges less. And I wish this were the one in the standard library. On the other hand, we have compare less, for which my version looks like this. And I believe this does match the specification in the standard library. The first thing we check is, are they both signed types or both unsigned types? All right. Either both signed type claims are true or both signed type claims are false. In either case, I can just do a plain old comparison of left less than right because the language knows how to do that. But if one is signed and the other is unsigned, we have some work to do. So if it's the left operand, or I should say the first argument that is signed, then we check to see if it's negative. Well, if it's negative, it's clearly less than whatever value is on the right, since that's unsigned. So we return true. Otherwise, I convert the left value to its unsigned equivalent and do a strictly unsigned comparison, which is safe because I know that the left value is not negative. And the third case is, again, we have one signed and one unsigned, but in the opposite order, and I do the equivalent logic. And those are the three cases for comparing integer types, values of integer types, even when one is signed and one is unsigned. For is less, my version looks approximately like this. I have values of standard arithmetic types. It is specified to do floating point comparison. So first, I find a common floating point type. And although I'm not showing you this meta function, common floating point t, if there's an integer type involved, it gets converted to double. And if it's a floating point type, I just make sure they're both the same. So float, if I have a float and a double, I make them both into doubles, etc. Then get values of that common type. And then we finally do a comparison of x less than y, assuming that the values are ordered. Now, we could just let it go by saying x less than y, but there is the possibility, if I have a nan involved, I could be raising a floating point exception because nans are not ordered. So by asking whether they're both unordered, whether in fact they are unordered, I can return a false directly. Right? They're unordered, so they're not in order. So is less is false. And that way I avoid the possible exception, floating exception. That brings us to total order. Now, the total order predicate is based on bit patterns more than anything else. The big picture is that it requires the ordering be from most negative to least negative, followed by least positive to most positive. But within those groupings, first all negative values, of course, then all positive values in the opposite order. Within the negative values, first we have all the negative quiet nans, then all the negative signaling nans, and they're each ordered according to their payload bits. Then comes negative infinity, then all the negative normalized and denormalized numbers in order of their value, and finally negative 0. And that completes the negatives. Positives are the same in the opposite order. First comes positive 0, then all the positive denormals and normalized numbers in value order, and then positive infinity, then the positive signaling nans, and then the positive quiet nans. So it's a restatement of what IEEE total order requires. Now, consider the layout of an IEEE floating point number, keeping that in mind. It starts with the traditional scientific notation, but IEEE decomposes, rebases, reorders, and then adjusts the parts. The most obvious is we change everything to bits, so we have base 2. But if you have a 32-bit floating point number, there's a 1-bit sign, an 8-bit exponent, followed by a 23-bit mantissa. If you happen to have a 64-bit floating point number, the layout is the same, you just have more exponent bits and many more mantissa bits. And if you've ever wondered why they are in that order, what if we treated those bits as if they were a 32-bit int or a 64-bit int or even a 128-bit int if you use a 128-bit long double? So keeping that in mind, here's my version of IEEE's total order. It looks like that. If the sign bits aren't the same, I get my answer immediately. Otherwise, find the first integer type of either 32, 64, or 128 bits that's big enough, do a C++ 20 bit cast to take those floating point values and have access to them as bits. And then I can return by asking you in order in the correct sequence by inspecting the sign bit. Okay? If you're interested, you can look at this in more detail later. I have just about 5 minutes left, so I have time for what I'm going to call a bonus algorithm. I started the talk with min and max, so I'd like to return to that. But suppose I need both of them, which are collectively known as the extrema. Now, of course, one approach is to reuse min and max. And so my min-max algorithm would look approximately like this, right? I can directly return a pair consisting of first the min and then the max of A and B. But of course, if I do that, I'm going to end up making two calls to the less than operator. I really only need one. It's cheaper to make one call than two. And if I do that, my code just looks like this. If A and B are out of order, return the pair B comma A. Otherwise, we return the pair A comma B. Let's generalize this. Suppose I want the extrema given a sequence of values. This is found in the algorithm header, where it has the name min-max element. We're given a pair of iterators, first, last. And it returns a pair of iterators in that range so that little m, which comes first, is in fact the first iterator whose corresponding value is the smallest, while capital M is the last iterator whose corresponding value is the largest. With n as the distance from first to last, we can certainly make separate calls to min and max. And if I do that, I'll end up with approximately 2n calls to out of order, which means 2n calls to less than or equivalent. But it turns out there's an algorithm by Ira Pohl from 1972 that reduces the coefficient by a quarter. So I'd like to share that with you very briefly. We're given two forward iterators, F1 and F2. Let's invent a precedes function that returns the truth of the claim that the respective values are less than. Then on top of that, I put an out of order that does the right thing, as discussed earlier in this talk. We have a max and a min function, which I really should have named itermax and itermin because they're taking iterators, not values. And they call that out of order. And now let me invent some notation, mm, to denote an ordered pair of iterators. And I'll invent a function min-max that makes such a pair as described in the code below. If they're out of order, then F2 comma F1, otherwise F1 comma F2, pretty straightforward. And a function meld that takes two of these mm pairs and produces one by invoking these itermin and itermax on the respective values. Now, if you look very carefully, how many calls will there be to precedes? There are going to be 3. In 3 calls to precedes, I'm going to process 2 iterators. That's much better than 2 calls per iterator, which would be 4. Okay? And what we're left with is just the logic of Pohl's algorithm, most of which is for special cases at the beginning and at the end. So here's a using, here's the introduction, handles the case where the sequence is empty or the sequence has only 1 item in it, which I've called a singleton. Otherwise, we have at least 2. So minmax of the first 2 is my initial guess. And now I have 2 cases. Have I run out? Then return my answer so far. I'm done. Otherwise, I found an odd item. There's a final singleton. So I've got to do 1 last meld and I can return the result of that. Otherwise, there's the general case. Meld the results so far with the latest pair. And with that, I think my time is up. I thank you all very much. I hope you've enjoyed this talk. If you have questions, I will hang around in Discord for a bit, and I look forward to chatting with you there.